Hello dear students, welcome again to the tetrahedron chemistry classes. So dear students, this is my second lecture on molecular orbital theory, lecture number 2, right? And in this today's class, I'll discuss the salient features of the molecular orbital theory, and then I'll apply all these features to the particular molecule to get the results, right? The bond order of the molecule, the magnetic behavior, the magnetic moment, and many more things, right? But before going into the details of the molecular orbital theory, if you are new here watching video for the first time, my suggestion is that please watch lecture number 1, which is the linear combination of atomic orbitals. You can see the link is flashing on the right top corner, and I am also giving you this particular link in the description section as well, because it is very, very important to understand the concept of linear combination of atomic orbitals before going into the details of the molecular orbital theory, right? So let's start molecular orbital theory, and these are the salient features. I have written these salient features in my own words, or it may be possible that you may not be able to find all these features in any particular textbook, because I have summarized all the things which generally used in the molecular orbital theory, right? So the first important feature is that atomic orbitals combine to give the molecular orbitals. Please remember, whenever you apply the molecular orbital theory, in that case you will apply the atomic orbitals of the two atoms, right? Two or more atoms, because why I said two atoms, because I am discussing diatomic molecules right now. Later in the classes, right, I will also discuss the polyatomic molecules. So whatever, say for example, if you are having the hydrogen atom and you are combining two hydrogen atom, right? Say for example, say I can explain you this particular point here. This is your hydrogen, which is the atomic number of 1, and electronic configuration is 1s1, right? So you will have these two kinds of these two different hydrogen atoms, both having the 2 electrons, and these two s atomic orbitals will combine to produce the molecular orbitals, right? So this is the first feature, which is the very, very important one. Atomic orbitals combine to give the molecular orbitals. Second one is the atoms are monocentric while molecules are polycentric. Again, it is very, very important. You see, if you consider only the atom of the hydrogen, that means this hydrogen atom is having, this hydrogen atom is having only 1 electron, right? Because its atomic number is 1. Since the atomic number is 1, so only 1 proton is there in the nucleus as well. So this particular electron in the hydrogen atom, which is present in the 1s orbital, is under the influence of one nucleus only when you say it is the hydrogen atom. But when you combine these two, right, this hydrogen atom and this hydrogen atom, and you form a particular bond, for say you form particular molecule H2. Now you can see here, this will have the 2 electrons, right? In the Lewis dot structure, you have studied all these things. So now these 2 electrons actually are under the influence of the 2 nuclei, one nuclei of this particular hydrogen and one nuclei of this particular hydrogen. That's why it is said that molecules are polycentric, because they have the more than one center. So this is the point number 1, this is the point number 2, right? And now I am going to discuss the third point, which is another very, very important. Number of the molecular orbitals formed are exactly equal to the number of combining atomic orbitals. So here I have written MOs. MOs stands for the molecular orbitals, and AOs stands for the atomic orbitals. And the very important feature is that whenever you combine to atomic orbitals, so whatever the number you are combining of the atomic orbitals, they will result the same number of the molecular orbital. For example, this is your hydrogen atom, 1s atomic orbital of this particular hydrogen atom and 1s atomic orbital of this particular hydrogen atom. That means you are combining 2 of the atomic orbitals, so they will produce 2 molecular orbitals. Similarly, if you are combining 4 atomic orbitals together, so it will produce 4 molecular orbitals, and so on and so forth, right? So third point is also clear, right? Number of the molecular orbitals formed are exactly equal to the number of atomic orbitals. Now my point number 4, out of the total molecular orbitals formed, half of them will have the lower energy than the combining atomic orbitals, and these are called the bonding molecular orbitals. Rest half of the molecular orbitals will have higher energy then the combining atomic orbitals, and these are called anti-bonding molecular orbitals, right? Please remember, see, this fourth point is another very important and the special feature of the molecular orbital theory, right? So how we can explain this third point? However, fourth point, I'll explain this fourth point again when I draw the molecular orbital diagram for the particular molecule, but right now you can understand in that manner. Say these two atomic orbitals are combining, right? So they will produce the two molecular orbitals, right? They will produce two molecular orbitals, two MOs. And out of these two MOs, one MO will have higher energy, right, than these two atomic orbitals, and another one will have the lower energy than these two atomic orbitals, right? So lower energy molecular orbitals are always known as the bonding molecular orbitals, as I have explained in the linear combinations of atomic orbitals, right? And higher energy orbitals are called anti-bonding molecular orbitals, right? Because in that case there occurs attractive forces, that means not attractive forces exactly, but in that case the maximum area of overlapping would be there when the two atomic orbitals combines, which gives the increased attraction between the electrons and the other two nuclei, right? And since the attraction brings down the energy of the system, that's why this lower energy orbital is called the bonding molecular orbital. Similarly, in anti-bonding orbitals, both the nuclei are exposed, as I have explained in the linear combinations of the atomic orbitals. These two nuclei are exposed to each other, so repulsion would be there, and due to this repulsion, the energy of the system increases, right? That's why high energy orbital is called anti-bonding molecular orbital, which I have written here. I hope this point is quite clear right now. If you if you are new here watching and learning molecular orbital theory for the first time, especially if you are in 11th class basically, or say not in 11th class exactly, in whatever class, whether you are doing BSc or MSc, whatever, and you are trying to learn this concept for the first time, if you find it a little bit difficult to understand the fourth point, don't worry, I'll explain each and everything when I'll construct the correlation diagram or the molecular diagram, right? Now, next very important point is what you can see here. Symbols used for the molecular orbitals are sigma, pi, delta, etc. See, for atomic orbitals, see if you are having the atomic orbitals, I can write here atomic orbitals, right? If you have the atomic orbitals, then for atomic orbitals, your symbols are what? Simple alphabet. S, that is sharp, P, right, and then D, diffuse, P is the principal, right, and F is the fundamental. Okay, so these are the full form, right? S, P, D, F. These are the alphabets used for the atomic orbitals. But when you have the molecular orbitals, then you will have sigma bond, then you will have pi bond, then you may have the delta bond. However, in these diatomic molecules, we will not see any deformation of any delta bond, but we will see the formation of the sigma and the pi bond regularly, right? I hope this fourth point is also clear. The fifth point is also clear. Now the point number 6, like atomic orbitals, molecular orbitals can also accommodate only maximum of 2 electrons, right? What is the meaning of that? The meaning is quite simple. For example, you are having lithium atom. It is having the atomic number of 3. So we will write the configuration 1s2 and 2s1. So what is the maximum capability of this s orbital to accommodate electron? Only 2 electrons it can accommodate. So like your atomic orbitals, your molecular orbitals, whether it is sigma or pi or delta, whatever, they can maximum accommodate only of the 2 electrons. So the 6th point is also quite clear right now. Now the point number 7, filling of these molecular orbitals follows Aufbau principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. See, in your atomic structure, when you learned your quantum numbers, right? and the filling of the atomic orbitals, right? Then what will happen? You first of all, you must follow the Aufbau principle, which is the building up principle. Aufbau is the German term which is known as the building up. So according to the Aufbau principle, what happens actually in the atomic orbitals? The atomic orbital which have the lower energy will be filled first, right? So here again in the molecular orbitals as well, your lower energy molecular orbital will be filled first, and it will also follow the Pauli's exclusion principle. That means any two electron in the same molecular orbital can never have same set of the quantum numbers. Spin quantum number must differ if other three are equivalent. So this will be followed in the filling of the molecular orbitals as well. And then lastly is the Hund's rule of maximum multiplicity. What it says that in case of the atomic orbitals, whenever you have the two atomic orbitals available of equal energy, then both will get single electron with parallel spin first, and then after your pairing would occur. Same rule here will also followed in the filling of the molecular orbitals. If you have the two or more molecular orbitals with the same energy, then all will get the single electron with parallel spin. Only after that the pairing would occur. So all these three rules would be followed in case of the molecular orbital in the molecular orbital diagram, filling of the electrons in the molecular orbital diagram as well. So this point is also clear, right? Now you know this hydrogen is having single bond between the two hydrogen atoms. Hydrogen molecule is having like that. If you have oxygen atom, you know oxygen is having double bond between the two oxygen atom. If you have the nitrogen molecule, you know nitrogen is having triple bond between the two nitrogen atoms, right? It is quite clear right now. This is known as basically bond order. This single bond is what? This is bond order. Similarly, this double bond is also known as the bond order. This triple bond is also known as the bond order. So how we can calculate the bond order with the help of the molecular orbital theory? Again, it is very important point. Bond order of the molecule can be calculated by this formula. Bond order equals to Nb minus N star divided by 2, where N is the number of electrons present in the bonding molecular orbitals, right? And N star, generally when you put asterisk or the star over the N, it shows the anti-bonding nature of the orbital. So this star means anti-bonding nature of the orbital, and this Nb means bonding nature of the molecular orbital. However, I made a little mistake. This B should be present on the superscript position, right? So number of electrons in the bonding molecular orbitals minus number of electrons present in the anti-bonding orbitals, and this when these two when you take the difference of these two and divide them by 2, then it will give you the bond order. If you don't understand, if you are finding difficult to understand this thing, don't worry, I'll explain all the things in the later, right? So I hope this point number 8 is also clear. Now there comes the point number 9. See, the very important and the distinct feature of molecular orbital theory is that it predicts the magnetic nature of the molecule. Say if you have the hydrogen molecule, see if you keep this hydrogen molecule in the magnetic field, right? So magnetic field can do two things with it, right? One, it can this molecule can be attracted by the molecule external magnetic field, or it can be weakly repelled by the external magnetic field. These two things can be done with hydrogen, oxygen, nitrogen, or any other diatomic molecules, right? This shows the magnetic nature. So this magnetic behavior can be very beautifully explained with the help of the molecular orbital theory. So magnetic nature of the molecule predicted by analyzing the molecular orbital diagram of the molecule. See, if you have hydrogen, oxygen, or nitrogen, or any other diatomic molecules or polyatomic molecules, what you will do, you draw the molecular orbital diagram of that particular molecule. This is molecular orbital diagram is also known as the correlation diagram, right? Once you form the correlation diagram or the molecular orbital diagram, then by observing, by analyzing this molecular orbital diagram, you can predict the magnetic nature of the molecule as well. So first, see, based on this magnetic behavior, your molecule may be of two types: diatomic molecules. Please remember, diatomic molecules are those molecules, if you keep these molecules in the external magnetic field, such molecules are weakly repelled by the external magnetic field, right? See, Now, what you will do to predict the magnetic behavior? If all the electrons are paired in the molecular orbitals, right, then the molecule is diamagnetic. That is weakly repelled by the external magnetic field. Okay, so whatever the molecule, see, sigma pi bonds are there, see, sigma and pi molecular orbitals are there. In these molecular orbitals, if all the electrons are paired, right, then your molecule would be diamagnetic and it would be weakly repelled by the external magnetic field. Next important thing is the next important magnetic behavior is the paramagnetic nature of the molecule. That means such molecules, when you keep these molecules in the external magnetic field, then these are weakly attracted by the external magnetic field, right? So now again what you see, you check the sigma and the pi molecular orbital in the molecular orbital diagram. If one or more electrons are unpaired in the molecular orbitals, then your molecule is paramagnetic in nature, that will be weakly attracted by the external magnetic field, right? Since now suppose say in any one of your molecular orbital diagram you are having one unpaired electron, in another, for another molecule say you are having two unpaired electron or ion as well, right? See, this molecular orbital theory is not only applicable to the molecule, but it is also applicable in the molecular ion as well, right? So say for example, in the first instant only one unpaired electron is there, so when one unpaired electron in the molecular orbital is there, so it is paramagnetic in nature. If two unpaired electrons are there, again it is paramagnetic in nature. But what would be the magnitude of the paramagnetic nature? This would be calculated by the magnetic moment of the molecule, and that magnetic moment will only will be your spin only magnetic moment, because here we will not consider the orbital contribution to the magnetic moment, which generally happens in the coordination compounds. In the coordination chemistry playlist, I have explained all these things pretty clearly. So if you want to calculate the magnetic moment of the molecule, you will use this particular formula. Magnetic moment mu equals to under root of n multiplied by n plus 2. Okay, so that means n is the number of unpaired electrons, where n is the number of unpaired electrons. So I am writing here number of unpaired electrons. Okay, so this is how you can calculate this thing, right? So this is looking like 3 now, so I am deleting it, right? So n times n plus 2. So these are the 9 very important features of the molecular orbital theory. We will apply all these 9 salient features on the particular kind of the molecule to understand this molecule, to grasp this molecular orbital theory completely. But before going into the details of the molecular orbital diagrams, it is very important to understand the formation of sigma and the pi bond. How we can form sigma and the pi bond in the molecule, right? So moving to the next slide, right? Please remember, whenever two s orbitals are combined, see, s orbitals are symmetrically distributed among all the axes. So I am writing here s orbital symmetrically distributed among all coordinates. That means in the x-axis, in the y-axis, as well as in the z-axis, this s orbital is cylindrically symmetric. This is the region s orbital when combines with any other orbital. Say for example, if s combined with the s orbital, it will always form sigma bond, because it is cylindrically symmetrical among all the axes, right? It should be along, not among. This is along all the axes, right? And when s combines with the p, it will also form your sigma bond. So s will always form the sigma bond, right? Now suppose you are combining two of the s orbital, then definitely one will be your bonding sigma, which I will write sigma b, and another would be sigma anti-bonding, which I'll write sigma star. Of course, bonding will have lower energy, I am writing here, okay, and anti-bonding will have higher energy, as I have explained in the theory. Okay, Now how we can construct? See, because this s orbital is cylindrically symmetrical along all the coordinates, so whenever they combine form the sigma bond. So this is positive overlap. That means it is constructive interference. That's why I said if you are new here watching video for the first time, so it is very important for you to learn the linear combinations of atomic orbital concept, right? But if you have followed my first lecture, then it is very easy to you understand all the things. So this is the positive overlap, constructive interference. That means these two are added, right? Positive phase and positive phase. When these two are added, what will happen? All the, see, this is the nucleus, this is the nucleus, and this positive charge showing that it is constructive interference. And you know, whenever the constructive interference is there, then your bonding molecular orbital is there. So I have written B over there. I have written B over there, right? And then after that, you are having negative. That means now you are subtracting, your wave functions are getting subtracted, right? Say, let me write once more. If you want to know the wave functions of this psi antibonding molecular orbital, how it can form? Psi A minus psi B, right? Since you know this is actually the subtraction, so this subtraction is happening here. But if you want to know, if you want to form your bonding molecular orbital, then your two wave functions of the atom gets added together, right? So this is your bonding interaction. So when this addition overlapping is there, this positive sign is showing the addition, what will happen? This particular region will have the maximum electron density, and when it will have the maximum electron density, then what will happen? These two nuclei are shielded by this electron density, and there would be less repulsion, and when the less repulsion is there, energy goes down, and bonding molecular orbital, sigma bonding molecular orbital will have lower energy, right? But, and you can see here, I have written G over there, where G is the mathematical term. So G means basically even, okay? And the name of G is the Grad, right? Grad means centrosymmetric, I, center of inversion. See, you may call it center of inversion or center of symmetry, like that, right? So whenever your system is having this I, that means center of symmetry, then your system is Grad or the even. So that's why this G is written over there, right? Because see, you can see here, this is having the center of symmetry, right? Because if you move along this particular bond axis, right, then you will find the same sign. See, positive here. So let me change a little bit. Positive here, and this is again positive here. But when you are combining these two these two wave functions, so what can happen in that case when you subtracting these two? So this one and this one, this is having positive sign, this is having negative sign. When this happens, so there occurs a node in between these two, right? This is known as the node. And you know the node is the volume where the probability of finding the electron is 0, right? So here what will happen when you subtract these two, right? So there occurs node. See, this is the molecular axis, and perpendicular to the molecular axis, there would be this node, right? This is nodal plane, right? This is node, and when this node is occurring, then your molecule is not actually, this is not having the center of symmetry. Center of symmetry means, see, when you start traveling from the one side of the any system, right, and reaching to the center of that system, and then you travel again in the opposite side or the next side of that particular system, but to the equal distance. If you find the same sign, then system is said to having center of symmetry, where, see, here electron is there, electrons are there, so negative, you know, and so this is having the center of symmetry, right? So that's why it is G rate. But here you see, because we are subtracting, so this will have the positive phase and this will have the negative phase, right? So this is positive. Now you are moving from here to here, going to the center of the molecule, which is the bond length actually. And after that center point, you are again moving in the opposite direction but to the equal distance, or you are encountering with the negative sign. The signs are different. That means it is uneven, right? It is uneven. When it is uneven, then it is known as the ungerade. This is known as ungerade. Ungerade. Ungerade, or you can say odd. Right? This is the concept of the center of symmetry. So whenever you combine the two s atomic orbitals, it will result in the two molecular orbitals. One would be the gerade, which would be the bonding one. Other one would be the anti-bonding one, that would be ungerade. Right? I hope this is quite clear to you. If you don't understand this thing, then you should learn about the center of symmetry, and I am giving you the link in the description box of my organic chemistry lecture where I have explained the center of symmetry very beautifully. I hope this is quite clear to you, right? So this is the s orbital which is combining here. Similarly, when s orbital combined with the p, as I have explained to you, it will also form the sigma bond, right? Now, see, this you can leave, right? Because this is the s, this is the p orbital, this is also the p orbital. This I am explaining in the next slide. That's why I am not touching here. Right. You can see here. See, this is something very, very important which you need to understand, right? So formation of the, see, you know, if you have, say these p orbital, this p orbital, so this p orbital, as you know, it is the dumbbell shaped, so it will have the px orientation along the x-axis, it will have the orientation along the y-axis, and it will always have, it will also have the orientation, orientation of the dumbbell along the z-axis, right? So px, py, pz. Now the question is that which one will form the sigma bond and which two will form the pi bond. You know, first bond is always the sigma bond whenever the bond formation occurs. Wherever the bond formation take place, first bond is always sigma, please remember. And then if the other two p orbitals are there, then the two pi orbitals, two pi bonds will form. Now the question is that which one will form, whether px will form the sigma bond, py or the pz will form sigma bond. If you consider px is forming sigma bond, that means these two form the pi bond. If you are considering py is forming the sigma bond, right, then these px and pz will form the pi bond. If you consider pz is forming sigma bond, then px, py will form your pi bond, right? So to explain the formation of the sigma and pi bond, I am giving you the video of mine where I have explained how we can form these two. But remember, whatever I am explaining, this is in principally this is correct. But for diatomic molecules, please remember, for diatomic molecules which are linear in nature, generally pz orbital form your sigma bond, and rest px, py will form pi bond. So please remember, for diatomic molecules, right? Diatomic molecules I am writing. Diatomic molecules, your pz orbital forms sigma bond, while your px and py form your pi bond. Please remember, this is very, very important, right? And watch that particular video. To understand which p orbital will form the pi bond and which will form the sigma bond, let us consider certain things, right? Say for example, these are my three fingers which all are perpendicular to each other, and let us say this particular finger, right, which is the middle finger, let us say it is the x-axis, right? So of course this is the positive lobe of the, or positive axis, plus x-axis, and just opposite this one, right, here there would be the minus one. And perpendicular to this x-axis, let us say this particular index finger is your y-axis, right? And perpendicular to these two, this is my z-axis. So this is my x, this is my y, and this is my z-axis. Say this is your px orbital, this is your py orbital, and this is your pz orbital, right? And now say another, you are having next set of the p orbital. This is your px, right? And this one is your py. and that thumb is the pz orbital. Now if I consider my x-axis is the internuclear axis, so that means px orbital will form the bond first, and they will come axially, right? X-axis and x-axis, they will come axially, and they will combine like that only. This is head-on overlapping or the axial overlapping. And you know, whenever the axial overlapping or the head-on overlapping takes place, in that case where sigma bond is formed. So this bond is the sigma bond. Now this position is fixed and this is the rigid one. Now for these two y-axis as well as for these two z-axis, there are no chances of forming bond by overlapping axially, coaxially or head-on overlapping. So what they will do, they will overlap laterally. So lateral overlap would occur in between these y-axis, right? So this will form your pi bond, and similarly this z orbitals, again they will form your pi bond because they will again overlap laterally. So it depends on the thing which axis you take as the internuclear axis. Now let us consider you are taking your z axis, right? This is your z, my thumb is the z axis, and you are taking this z axis as the internuclear axis. Now what will happen in that case? So in that case your z orbital will come first, right? Like that, your z orbital will come first, and z orbital will form your sigma bond, and then your x and y will form the pi bond. So this is how you understand. See, there is a great confusion among the newcomers or the new students that which p orbital will form pi bond and which p orbital will form the sigma bond. It purely depends on you, right? Which axis you take as the internuclear axis. If you are taking x-axis as the internuclear axis, then it will form the sigma bond, and then py and pz will form the pi bond. If you are taking pz as the internuclear axis, then your pz orbital will form the sigma bond, rest two will form the pi bond, and same is true for the y orbital as well, right? So whatever book you are studying or from which book you are taking this reference, and sometimes you can write the reference of that book also in your examination, right? I hope now you understood how we can form the pi bond and the sigma bond by using the p orbitals. Okay, so I hope you have watched this particular video and you have grasped the things where I have explained how the sigma and the pi bonds are formed. But some of you may still wondering why this is happening, why this why this z orbital is forming your sigma bond in case of the diatomic molecules. Please remember, diatomic molecules are linear in nature, and in this linear molecules, your molecular axis is the z axis. Please remember, for linear molecules, z axis is taken as the molecular axis, right? And that's why the z orbital will form the your sigma bond, and pxpy will form your pi bond. But in principle, anyone can form sigma, anyone can form pi. Why we are choosing? See, there are certain reasons. First of all, the symmetry, right? Linear molecules have the cylindrical symmetry around the bond axis, and bond axis is actually along the z axis. That's why we are taking this one. And next, when you consider this z orbital as the molecular axis, so atomic orbitals overlap along the z axis, this will form the sigma bond, right? And see, it is our convenience as well. Choosing z axis as the molecular axis simplifies the molecular orbital diagram and lots of calculations involved, right? These are the three regions. That's why we adopt these things, and this has been adopted by the IUPAC. Please remember, IUPAC recommend that z-axis convention for the linear molecules, whether it is hydrogen, nitrogen, oxygen, carbonyl, acetylene, whatever is there, z orbital will form your sigma bond. Please remember this particular point, right? Now I am coming back how actually the bonds form. See, this is my x-axis, this is my y-axis, and this is my z-axis. The condition is that, like in my video where I have explained with the help of my two fingers and one thumb, right? The 90-degree perpendicular relation of these axes, but here I cannot show because it is the 2D, right? So here you see this is px, perpendicular to this is the pz, and see this py is basically I have shown you here, but it is coming out of this particular board and it is going below this particular board, right? So all these are at the 90-degree angle. So this is one of the pz orbital. Please remember, this is one of the pz orbital, and this is the negative coordinate or the negative axis, right? And this is the positive part, and this is your second pz orbital. Now I am combining these two. So here you can see plus and plus, they both are combining, they are combining with the same phase. When they are combining with the same phase, it is a kind of the bonding interaction, right? When the same phase are combined, it is the bonding interaction, and this will increase the electron density. So here we are adding together plus, right? See wave function of this, and I am adding the wave function of this pz to this particular pz. That's why plus I have written here, as I explained in my last slide. So here you see this is your pz, right? This is the bonding interaction. See, and see here you see this is your molecular axis pz, and perpendicular to this you see this is what? This is the nodal plane. This is the node. So p orbital is already having one node, and this p orbital is also having the one node. So whatever the molecular orbital will result by the addition of these two, that molecular orbital must have these two node in that molecular orbital as well, right? So this is the node which is this one, and this is another node which is this one. So these two nodes were already present in the two orbitals. That's why they are present in the molecular orbital as well, but new node is not forming here. That region is the maximum electron density region. These are the two nuclei which are well shielded by the electron density which is present here actually. So this is the bonding interaction, and it is the G rate, right? It is the G rate. Why it is G rate? See here, why this bonding interaction is the G rate in that case? Because when you combining these two, so plus is combining with plus this one, right? So here if you move from here to here, right? See here, if you are moving from here to here and coming to the center to this one, and then you are moving equal distance in the opposite direction, you are encountering with the same sign, negative and negative, right? When same sign is there, that means center of symmetry is there. When center of symmetry is there, then it is said to be G-rayed. That's why sigma bond G-rayed type. But this is the bonding interaction. Similarly, you can subtract the two wave functions as well. So this is the pz, which is these two pz are subtract, wave functions are subtracting. We are subtracting the wave functions. When this happens, you know, one node is present in the one in here, one node is present here, right? And then we are see how we can. Let me draw very quickly like that. Say this is my pz, this is another my pz. Here in that case, plus sign is in the back side, negative sign is here, and here you see plus sign is here and negative sign in the back side, right? So in that case you see positive phase is overlapping with the negative phase, right? That means one node will be present here again. One it has to cross. If these two can combine, then they must cross the nodal plane once, right? When they cross the nodal plane, that means that plane would be here. So one node is here, another node is here, and new node will form between the molecular axis. Please remember, between the molecular axis. So this is how I have subtracted. This is the original node which was present in the pz. This is the original node which was present in the pz. This is the new node which we form by the negative destructive interference. That means opposite sides are matching with each other, right? And say now if you want to check the whether it is G-rayed or un-G-rayed, so you start from this particular end, right? Move to the center of the molecule here, and then again in the equal distance in the opposite direction you move, you find a different sign. Plus is here and minus is here. That means it is not centrosymmetric. That means it is un-G-rayed. That's why this anti-bonding interaction, which generally formed by the negative sign, right? Negative. That means differences in the wave functions. So it is ungerade anti-bonding. Here you can see in that case, see this is plus, this is also plus, right? This is minus, this is also minus. Clear? And this is, you see, this is your what? Ungerade one. This is ungerade, right? Here, right? And this is the gerade one. If it is not clear, this diagram is not particularly clear to you, then you can stick on to this one, which I am explaining to you. So sorry, not this one, to this one. Forget about this one. I am explaining the sigma bond, right? You see here, this is plus, this is also plus. So I am writing here. See, this is plus overlapping with the plus. So centrosymmetric. This is the center. And you are moving from this end, going to the center, and moving to the opposite end, going to the center. Positive, positive you are encountering. That's why it is gerade in nature, sigma gerade, right? Right. But when you subtracted, this is minus, this is plus, this is minus. So I can write little bit bigger plus minus. So this is plus, this is minus, right? And when you are moving from here and going to the center, and then again moving to the equal distance in the opposite direction, you are finding your negative signs, that is, it is ungerade, right? This actually I have taken from the Advanced Inorganic Chemistry by Shriver and Atkins, right? This diagram I have taken from that particular book, so credit goes to that particular book, right? So this is how you can form. So I hope this is quite clear to you. Now, since your Z orbital, your sigma Z orbital already formed your sigma bond, rest 2 will form the pi bond. So if you want, then you can write sigma Z here, sigma Z, like that. Okay. Now your px and py, the other 2 will form the pi bond. Here you can see the interaction. Say this is my px orbital, this is the x-axis, this is the positive lobe, this is the negative lobe. And again you see this is my another px orbital, this is the positive lobe and this is the negative node, right? This is how you can see. And these two are combining right now, right? So plus is combining with the plus if we are adding the wave, if we are adding the wave functions of these two, so it will result the increased electron density in that particular region. Similarly, negative is actually combining with the negative. So here again you see this is the negative, but electron density is there. And here you see original node present between the two atomic orbitals. So definitely when you form the molecular orbital along with, see, perpendicular to this molecule, this is the molecular axis now, perpendicular to the molecular axis, you will find this particular node which is earlier present in the these two atomic orbitals. So since they are laterally overlapping, that means this is overlapping to, see, let me take the different brush, right? See, this is the lateral overlap. This is how they are overlapping. You know the lateral overlapping will result in the formation of the pi bond, right? That's why this is the positive lobe of the pi bond, this is the negative lobe of the pi bond, and it is ungerade now. Why it is ungerade? Please remember, it is ungerade. Why it is ungerade? See, now if you start from here and go to the center of that particular molecular orbital and then again move in the opposite direction but to the equal distance, you are encountering with the negative, your opposite sign, negative and positive. That means it is uneven, that's why it is ungerade. So please remember, pi bonding molecular orbital is ungerade. But when you are subtracting these two, right, when we are subtracting these two, that means the wave function gets subtracted, then what will happen in that case? In that case, you see what I can do, I can write like that. So this is positive, this is negative, this is negative, this is positive, right? I am combining these two. When I am combining these two, this positive is combining with the negative to form the pi bond, this negative is combining with this positive. That means already they has to cross the nodal plane, right? So that will produce nodes here. So this is the node which is this is the node which is already, this is the nodal plane which is present in the p orbital, and this is the new node which is forming this one. And this is actually the gerade one. Anti-bonding is the gerade one. How this is the gerade one? Now if you start from this end and traveled from this end and goes to the center of this particular molecular orbital, and then again you move in the opposite direction but to the same distance, you are encountering or finding the same sign, that means it is even mean is this gerade. Center of symmetry is there. That means a center, see a center which is always present in the center of the molecular orbital, right? And it is giving you the symmetry of the two orbitals. That's why it is centrosymmetric, gerade one. And same is true for the negative sign as well. Remember, only one center of symmetry is there in any molecule. More than one center of symmetry cannot be present in any molecule or in the any molecular orbital, right? So this is your not centrosymmetric, that's why it is your ungerade. Sorry, this is centrosymmetric, that's why it is gerade one, right? So please remember, pi bonding is ungerade and pi anti-bonding is gerade. Same is true for the py orbital as well. Here you can see plus is combining with the minus, right? So this is ungerade, okay? But in case of the anti-bonding, minus e plus minus, as I have written plus and minus. So this is plus, this is minus. They are combining. So this is center of symmetry because it is negative, it is negative, it is positive, it is positive. This is how you can understand the formation of the sigma and the pi bond. It is very, very important to you.